Okay, so what I want to do, which seems an awful long time ago that we started this, but what I want to do is sort of take you through why larger benthic foraminifera are really important in our study of the collision with India and Asia. And what I'm sort of going to show you is that that these organisms, which occur in shallow water, nearshore shelf environments, that these organisms can then be used to define both the spatial environment and the geographic distribution, as well as the stratigraphic constraints as well. So I'm going to take you through why we're going to use larger benthic foraminifera, the paleoenvironmental significance of the carbonate facies that they're found in, and I'm going to show you and take you through a modern analogue that I've worked on, and then I'll come back to the to India, where we'll look at where we were correlating these tertiary sections around the spontane ophiolite. So as you'll recall from earlier talks, the one that when I was talking with Mike Searle, you'll know that Mike was and had lots of students working on the structural interpretation of the Himalayas. And one of the issues that they had was that there were tertiary sediments there which contain all these foraminifera. So that's how our collaboration started. So how are foraminifera used? Well, we can look at their geochemistry, their shell chemistry. We can get some isotope and trace element data from them. We can then apply this to both geographic and paleogeographic global and regional mapping exercises. Clearly, we can use them for the biostratigraphy. Taxa are used in dating of strata. And of course, there's a paleoenvironmental use that we can get out where taxa are used in determining both the habitats and niches in which they occur. Now, I'm just going to concentrate on a couple of these elements. One is the carbonate facies variations, which have been recognized through space and time. And this is really following on from the brilliant work done by a chap called Wilson in the mid-1970s. His work is still very relevant today when you're looking at carbonate facies variations. This allows us to recognize, shallow marine carbonate facies, which are quite different from the deep sea and the oceanographic ones, and that they're also very much dominated by these larger benthic assemblages, which were first sort of worked on by a chap called Lucas Hottinger in the 1960s, and then various people, including Hans Schwab in the 1980s, worked on sort of trying to identify the forams. But it was only the major work by someone called Sarah Keel, who in 1988 allowed us to use an erect biozonation scheme. And so we're going to look at just this biostratigraphic zonation. You'll appreciate the work that's done with the planktonic foraminifera. As I say, I will take us through the larger benthics. So the biostratigraphic use of benthic foraminifera. Well, you'll have seen diagrams like this one before, where we have time over on the left-hand side, getting progressively younger as we're going up, and then we've got ranges in which we can see particular forams, and we usually have what is known as a first appearance of it, and then a last appearance of a particular organism coming through, and that time segment where they're occurring in it, that can give us a dedicated biozonation for that particular taxa. But with larger benthics, we have a slight problem. Now this diagram, I know it's a bit busy, got an awful lot on it, but it is shows.
Excuse me, Owen.
Yeah.
I think the slides are not moving now. We are stuck up with the opening slide only.
Oh, you're stuck with the opening slide only. Oh no. Oh dear. God, this is terrible. Why is that?
Yeah, it's okay now. It's okay now.
Yeah, it's up to number 6. Perhaps I'll just have to do it like this.
Okay, now this will be a rehearsal and then we will redo it again one more time, okay?
Do you want me to go back to the
No, no, it's
beginning?
okay, it's okay. Please continue. No problem. It's okay.
You're okay from here.
Okay.
Okay. So I will just click on the slide. So this very busy slide, let me just take you through it. So at the top, the letters in or the numbers, sorry, which are in white, the little green boxes. These are the carbonate facies zones which have been recognised by Wilson, and we're going to be very much interested in sort of numbers from 9 down to about 4. That's where there's going to be an awful lot of change. And then I've added on to this some of the work that was done in the 1960s, which shows us a lot of the different assemblages that you're getting and where they occur along this transect when we're going along a typical sort of shelf sequence. So over on the right-hand side, we've got all our planktonic forms, and then to the left, we've got our larger benthic forms coming in. So this classification is sort of an idealized distribution of typical modern assemblages that we can see here. So let's just concentrate on this, the area that was to the left. So we've got a couple of diagrams here to look at. The top one shows a lot of the nearshore carbonate environments, and just beginning to show or explain to you how complex they are going across this, from the coastal area extending into a fully marine environment. And the bottom diagram, it shows you some of the topographical features which you might come across in these. So we've got typical ramp, banks, rimmed shelves and things. So they're very, very complex topographical sort of features. And when we're looking at them, so let's just remind ourselves what foraminifera are. These are single-celled organisms, and they all belong to the kingdom Protista. Their size range is from 0.02 up to 150 millimeters. In fact, they could probably even be larger than that. So they're very small and can be quite large, and they range up and down the strat column from the Precambrian to recent times. They're often considered to be sort of quite primitive because they've only got one nucleus, but they are by no means simple organisms. And some of the test shapes that we can see here, and this deep oceanic graphic form that we've got here, this Globigerinoides, it's a very complex sort of shape. So they usually have a shell, or what we would term a test, which is made out of a biomineral, usually calcite. The types of forams which have no test on at all, the most common one is amoeba, which is just sort of a sac of protoplasm. And they are wholly aquatic and usually marine in their existence. So let's just concentrate a little bit on the larger benthic foraminifera. There's a number of groups are studied in this division, including all those which are now extinct, the Fusiolinids, and then there are the modern day Ceratids and some Alveolinids, and the differences or how they're classified is all related to the wall structure. And also, of which there are sort of 4 types, which are seen here on this diagram in the center. There's some examples of there on the right-hand side. But you can see that there's, calcareous regular hyaline is now probably the wall structure, which is seen by a large number of larger benthics. Whereas at the top we've got calcareous microgranular. These are the ones which are now extinct, but which are usually sort of found in Paleozoic forms. So their morpho-shape differences are also quite unusual in that they can be disc-shaped, they can be ovate, they can be fusiform, and consequently their habitats might also be slightly different in that, yes, they're going to occur on shallow shelves, but they also occur in deep oceans as well. And I'll introduce you to an example which is from a deep ocean. So they're usually highly abundant and have a large diversity as well. And consequently, there's quite good, quite high evolutionary rates as well. So this makes them particularly useful as a biostratigraphic tool. So let me just introduce you to this gentleman, William Carpenter. So he was a Victorian zoologist. One of his greatest claims to fame was writing a book, a large tome on the microscope, and he was also one of the ecologists, geologists, or paleobiologists who actually studied foraminifera that had been collected from the Challenger expedition. Now, he didn't actually go on the Challenger expedition, but he did study the sediments when they were brought back to the United Kingdom. And I've got a couple of illustrations here which are really quite nice to just talk through. So you can see that the one on the left-hand side, this is a Discospirina, and it's a very large foram. It has a very, very thin test, but it occurs on the abyssal plains at over 3,500 meters in, this is water depth that it's occurring, which is actually pretty deep water. So certainly not a shallow benthic foram at all. And what you see on this whole specimen here, this nice pink specimen, is you see the stages of growth and evolution from its proloculus, which is this bit, this is the earliest stage in the center here, to these later chambers, which are added on in an annular sort of style around it. Now, the one on the right is also quite interesting because it's showing you another feature which the forams have, and that's the ability to regenerate. So you can see this central area here was obviously broken from a larger adult, but there was sufficient amount of the nucleus and protoplasm there that actually it could then regenerate itself and start adding on additional annular chambers. And both of these have been illustrated by Carpenter. In fact, the one on the right, I have the slide that Carpenter prepared there in the late 1870s. So that's just a brief introduction to forams. Now I want to move on to one of the modern day analog, which I'm going to use. And this is Florida Bay, which is in the southern tip of the Florida peninsula. And just from this satellite image, you can see that it's a complex area. It's a very large sort of bay, but it's sort of got this reticulate pattern which occurs throughout the bay, and we'll have a closer look at that in a little while. But just a few sort of facts about it. The Florida Bay itself is bounded to the north by the Everglades, which occur up here, and Cape Sable over here. To the east it's got Key Largo and this concentric chain of keys which follow all the way down, which is a now exposed sort of coral reef. And these extend right down into the Gulf of Mexico. But one of the interesting features, which I want to sort of just reinforce, is seen on this lovely Eb Fowler's sport fishing map of Florida. So all the pink areas that you can see on here, all these sort of banks, they are all water depths of 15 inches or less. So you can see that it's possible to actually walk across huge distances of Florida Bay, and I can tell you from experience that's what I've done. And between these shallow pink areas, we've got these blue areas that we tend to call lakes between them, and these are covered in sort of seagrasses, as we see down the bottom right in this diagram. And attached to the seagrasses, we've got these larger benthic forams, of which there's predominantly two main species. There's a few others as well, which I'll just introduce you to. But in the main, we've got these two, Androcena and Archaeus angulatus. Now, what I did, along with my supervisor, Martin Brazier, we did a sort of like a transect along here, which is seen on this map at the top here, following this red line, going through the bay and out to the outer patch reefs. And we've got three main species that we analysed here. We did some stable isotope work on this, going from this is the fully marine area, the top here, OPR, is the outer patch reefs, down to this one, EK, Eagle Key, which is right up here, just off the Everglades. And what we found with these, with our stable isotopes, that there was only a 2% depletion of oxygen along this transect, whereas when we looked at the carbon, there was a 6% enrichment of carbon along the transect. So what it's showing us is that there are specific niches that these forams will live in, and they sort of might cross over a little bit, but in the main, you've got Androcena here in the more restricted eutrophic areas in the north of the bay, and then as we get to fully marine areas, we're getting into this particular form called Cyclobiculina, which looks a little bit like the Discosporina. We managed to cross-check some of this isotope data from both Florida Bay, which is side indicated by A over in this diagram, and the B side we compared it with some forams that Martin had collected from Barbuda as well. And we noticed there was differences there, particularly in the growth of these things, or whether or not whatever they were living attached to, whether or not they were actually in sediment or actually attached to a seagrass or Penicillicea, which is a marine algae. So that was an interesting sort of thing to always bear in the back of your mind when we're looking at these. So now I want to bring us back to something which will be a little bit more close to home and sort of on topic for what we're going to discuss here, which is the dating and closure of the Tethys Ocean. So as you'll know, there's a number of ways of dating this, and it has been highly controversial over the years. So we've got indirect methods of dating, which is the granitic magmatism that's going on, and clearly that will give us an absolute date. There we've got the timing of the ultra high pressure metamorphism, and again, these are both of these two areas are ones that Mike Searle has had students working on over the years. Another group of researchers look at the post-collision molasse sediments that are formed. In other words, the first terrestrial sediments you've got, and that will also give you a date which is clearly a lot younger than the absolute dates from either the metamorphism or the granite emplacements. But what Mike suggested to me was that we have a better direct method of dating when India and Asia collided, and that was via the paleontology, looking at the youngest marine sediments that occur within the suture zone of the area. And this was the area that I was tasked with working in. This is the Spontane ophiolite up here in the north of Ladakh. Mike was having a student who was working on the ophiolite itself, looking at that. And he tasked me with going to look at some of the tertiary rocks there. And just as a brief reminder again, so this is where we are on our shelf. This is the sort of area that we're going to try and identify that might be occurring around in Spontane. In order to really look at this, this has sort of now been, I think it's sort of coming up for 20 years now, that there have been shallow benthic zonation schemes have been known and have been used, and that's this column, this grey column here on the right hand side of the stratigraphic column. So we've got typical ones which have been used in biostratigraphy before, the planktonic foraminifera here, the calcareous nanoplankton here, and now to this, just over 20 years ago, 25 years ago now, was added the shallow benthic zonation scheme. Now this was first devised in the Mediterranean, in the Adriatic area, and once this sort of tool had been established, I thought, well, this looks quite handy. I might be able to well use this in looking at material from the Himalayas. The simple reason being that a lot of the planktonic foraminifera, although they are quite abundant, they are often destroyed. So the final marine sediments, being these shallow carbonate areas, were going to be the ones which we thought that might be worth targeting. So we looked at a number of sections around the ophiolites, and the ones in red are the ones that we sampled and worked on. We then also took some already published data as well, and sort of tried to look at that in relation to it. Now, the reason for, when you go into a highly structural area, and you will know that it's an area that's got a lot of different topographical features, as seen in this beautiful sort of shot from the aircraft going over there. And when we actually look at down on the ground level, we find that most of our Paleocene and Eocene rich limestones are actually always at the top of the mountains. So it's often very difficult to sample a lot of these. We have to be in the right area to actually get samples which are in situ. One of the hardest things to sort out, because was actually in the intersuture zone. And I realised when I started this why a lot of people hadn't actually sort of worked in the intersuture zone. It's because most of the forams, most of the fossil material are actually very highly deformed. So not the easiest things, first of all, to identify or to actually work on and tease out the story of what was going on there. But anyway, we persevered, and then we managed to come up with this sort of section through there, and we were looking at a number of the different limestones which occurred along the Zanskar River. We had quite a good collection of material from there, and then around Spontane. And when we started there, we were getting a number of rocks which contain lots of nice material. The two at the top are the two macro samples. These are lovely nemulites and discocyclinids, and the black areas in here, these are alveolinids, which occur. And then if you look at this photo mark down here, you'll see that this is a numulite at the top here, alveolinid underneath it, but the boundary is almost fused between the two, very, very uneven, as one has sort of started to, as they've been almost welded together. A lot of them, like we see in this center, these are alveolinids, but they have been heavily deformed, a lot more so than the nummulites, because the alveolinids have a slightly thinner wall. These are the fusiform forms, of the ones that look a bit like cigars, and they're very damaged. There's a discocyclinid down the bottom, a lepidocyclinid down the bottom here, which has been fractured and broken. Discocyclinid in the middle here, which is slightly deformed as well. This is very, very typical of a lot of the rocks which we are going to find in this area. But what we have got is we've got some sort of diversity of material of the assemblages, which is really what we need. We don't need specific first and last appearances of these. What we need is an assemblage of particular forams together, which we can then put that into its particular shallow benthic zonal scheme. So we started looking at a number of sections around there, and this is a typical one from a place called Marlin, with samples, numerous material along there, particularly from the limestones. That's what was really interesting me, and I got some, as we would expect, some smaller benthics, almost planktonics, globerotallid type things, the Rosavella down the bottom of our sections, passing up into the top of the section where we've got alveolinids, asolina, which is an early sort of nummulite form, and discocyclina. One of the weird things about these forams is that even though asolina, which is a primitive nummulite, they do occur alongside other nummulites as well. In other words, later ones that they've evolved or that have been derived from them. So they're not specific as, say, some planktonic forams might be. So here we've got our section in Singichu. Again, much the same. We had some agglutinates down the bottom here, occurring in some of the limestones, then going up into some of our planktonics. Then, as we're going up through the section, so we're becoming progressively more and more shallower and closer to the shore. At the Gomba section, that repeats everything that we've seen before, as does our next one, our final section, Kanji as well, was exactly the same. We do get some sort of areas where there's no deposition at all, or nothing that can be discerned from that area. In other words, there's missing stratigraphy in there. But in the main, it was possible to sort of correlate between these two. So eventually, we managed to put our correlation together, quite complex, but we have this sort of sandstone that is between a couple of the big limestone beds, and then the very famous Kibling limestone and the Kessie limestone, as we called it, and these sort of transition beds which are going between the Paleocene and Eocene. We did do some, or I did some isotope work from there, but of course, clearly these rocks have been heavily altered, so they're not as, it's not as clear cut trying to get an isotope signal out of them, because they've all been overprinted with the with the tectonic processes that are going on The only thing that was sort of discernible from it was the sort of negative spikes here, which might relate to the Paleocene-Eocene boundary. We thought that was quite interesting, but there wasn't really sufficient data to sort of really add that into our paper. But of course, this is what I could work out from it. Once we got sort of all our assemblage data together, we could then work out where we were on this platform. So we had certain assemblages, the alveolinids, they're the near shore assemblages that we've got going into our nummulites, which might occur in some sort of back reef environment. There may well have been seagrasses that these things were living on at the time. We're not really too sure about that because we couldn't find any evidence of that, but it is considered that nummulites did live on attached to seagrasses. They certainly contain photosymbionts as well. And then as we're going gradually more into the shelf slope area, we're going from sediments which are dominated by nummulites, then asolinids, then this mixture of asolinids and discocyclinids, which we get in our deepest water before we pass into our planktonic foraminifera. So here's another just quick sort of look at some of the material again, because it is so attractive when you look at it in thin section and in hand specimen. This is a hand specimen, a surface of a bit of the Kessie limestone here, absolutely packed with biota in here at all, and I can see there's nummulites and alveolinids in here as well as discocyclinids and asolinids in here. And again, as I say, some of them show this sort of deformation that we're getting round here, and particularly the alveolinids. And there's another picture again of this one which shows this sort of fluted or fractured sort of boundary between the two, where you can imagine there's just a lot of heat and pressure on these is actually causing a lot of the carbonate to become remobilized. But you can still make out the actual form that's there. So what have we got around Swansea? Well, we've got a nearshore carbonate environment around there. I hope there's sufficient evidence there that you think, yep, I can see how this could have been a Florida Bay type environment where these organisms were living. Well, this work is all really Mike's sort of major contribution, and what he works on is where we put together an integrated chrono and biostratigraphic sort of section for it, and then got our age of our final sort of sediments, final sort of marine sediments that we could see in the Zanskar Ladakh area. And from that, Mike this has been sort of the labour of his love for years, and I take no credit for this at all. This is all down to Mike, this sort of interpretation of what's happening here. And it is the simplest thing. So we got these thrusts coming in, moving a lot of our tertiaries onto the higher topographical features, which is how we see them today. And clearly it was ongoing all during the Eocene and the Paleocene as well. And finally then, in the summary, we've taken this onto a much larger scale, where we've been looking at, in fact we're extending and have begun to extend our work into the Oman area, and we've also recently had a student who's worked down extending it into Myanmar as well, so going along that the southern southeastern sort of trend of when Tethys was closing there. And it looks as though within reason that a lot of this was all occurring at roughly the same time. sort of conclusions or summary of what we've got going on here. So the larger benthic ascendages provide an excellent tool in looking at the biostratigraphic control in these shallow carbonate facies. They've allowed us to do this. We couldn't have done this with just planktonic zonation schemes at all. We needed this larger benthic zonation scheme. And it's actually now been, I think there is someone who has been working on it in the Caribbean area as well, but they've not got to pass on acknowledgement to all my colleagues, both at Oxford and London University, who've helped me, including the late Martin Brazier and carbonate petrologist Dan Bezents, who I worked with out in Florida. We had various funding, both from the department and the students who I was with. Richard Caulfield, he got NERC funding as well. And I also got some assistance from the Royal Microscopical Society. So even a little society helped with funding for this work. With that, I'll say thank you very much, and I'll answer any questions that you might have. And I hope that's okay. Ritesh, thanks very much.
Thank you, Owen. It was a very interesting journey, I must say. Forums, yes, we have. I had collected them when I was student, in my college days, university days. Oh, sorry. Hi, Owen.
Hi.
So, thank you for the very nice presentation and taking us back in time. And forums, I think, in a one way, are the most, you can say, the living fossils of, huh?
Yeah.
Right from Precambrian to today.
Yes. Yeah. Our Precambrian work is quite interesting. That was almost a case of identifying things which weren't fossils in a way. It came about at a time when a lot of people were, where you saw in a lot of publications, people were always trying to get, to demonstrate that their fossils were older than someone else's fossils.
Mm-hmm.
And that's absolutely fine in one sense, but we were very fortunate in that the material we looked at from Australia was actually in the British Museum in London, and hadn't been looked at since it had been initially described. So we went up there and had a look at this material, and then brought it back to Oxford because it just didn't seem. I don't know. There was something about it which, then when we started looking at it in detail, which was painstaking, which was hundreds of hours of microscopy work on rock material. You'll know that looking at most thin sections, they are 30 microns in thickness, and so light will pass through them. We were looking at prepared. They were thick sections in that they were up to 350 microns thick, and some were then down to about, 150 microns. So it was really difficult to get light to pass through them to actually find these things which had been described as fossils. And then we started. So we were the first people to actually use a technique of imaging which enabled you to Z-stack, in other words, take different images through the focal plane and then piece these all together to get a final image that was all in focus. And this showed us that actually a lot of the artifacts that we were looking at, although they looked biological, they were actually just being formed along the edge of mineral boundaries.
Mineral boundaries.
And it was because they were all in cherts rather than any any other lithology, they were very, very difficult to sort of interpret. Um, so yeah, it was a strange, and the more we kept looking at them, the more we were convinced that actually these are not um, biological components at all, but they are abiological components. So we came up with this idea that in order to say something is biological, you've really got to um, demonstrate that it cannot be abiological, which was very, very difficult to grasp because a lot of people sort of were upset at, that their sort of observations were being questioned. But I think that's only right that, everything that you put out there, either publish or whatever, is open for debate. And it isn't just sacrosanct to say, well, actually, here you go. I've identified this as a fossil. No one else can question that.
Mm-hmm.
Whatever you're looking at, it's got to be sort of tested. And certainly there's, well, as you know now, there's more and more analytical techniques are coming on, and certainly a lot of people have looked at our initial work and have been working on sort of high resolution analytical techniques. I mean, even just, initially, say this is sort of like 20 odd years ago, there was this sort of belief that if you demonstrated that something had a carbon component to its geochemistry, then it must have been biological. And that, of course, is just not true. You've got to be so careful. And even if you can demonstrate that in a particular, certainly in an old Archean rock, that what you've got is biological, you have the other problem of working out just exactly how old it is. We can all, anyone who's worked in the sort of the Phanerozoic will know that if they've got a trilobite, it's going to be from the Paleozoic. And if you found one in younger sediments, you would know that it had been transported in. It was not actually in situ.
Yeah, actually works.
But if you have a rock that is, say, I don't know, 2,500 million years old, and you then have a fossil in it which is 1,500 million years old, you've got a huge problem. It is not really in situ.
Mm.
So, you've got to be very careful, I think, when you're looking at certainly these very ancient sediments to demonstrate that the organism or the component was actually contemporary with the rock, and is not an artifact from a much younger time period. As I say, when you're dealing with billions of years, well, what's a billion years between people when it's 2.5 or 3.5? But when you're dealing with sort of, as I say, rocks in the Phanerozoic, certainly if you've got tertiary rocks, you can recognise material which might be from, say, the Mesozoic and certainly the Paleozoic. And here we're only talking, 200 million years or the last 500 million years of Earth's history. So it's often, you do have to get this time frame sort of squared away in your mind as to actually what you're dealing with. Yeah, I don't know if that was. Anyway, sorry.
Yeah, it's quite fine, And can I ask you one more question?
Yeah, sure.
So I just wanted to know when you are dating these old specimens, 3.5 billion years. So the question always arises: 4.6 billion years the Earth originated. just this is a belief, But can we have a theory where when the Earth was cooling, we have these rocks being formed due to volcanic eruptions, or well, that is also another process, how the first rocks were formed, or how the yeah, that is another question. But when it was cooling, then the minerals were being formed, the water was being formed, and simultaneously these pri- primordial form of life, or primitive, the most primitive form of life, we can't even say whether it was life, as you said that all the life, we generally believe that it has to be near the carbonates, but you find it near the silicates, the church, and if yes, then probably the question is, was this evolution and formation of the land, or you can say the minerals, the water, maybe the last components, maybe the silica at the time when they were following the, or if we see the Bowen reaction series, or the quartz being formed in the last stage, then water, and then these primitive lives, the 3.5 billion years what you have dated. Maybe if we can find some more evidences, maybe these date back to the same time when the earth was cooling and the first form of minerals were being formed, and then silica, and then this water, and then this, and the same type. This is just an observation which I, since I'm making this museum, so I have to, I'm just thinking of the first form, how things were evolving. So all these theories, when we say that no, first earth formed and then this water will come and then this life will come. So somewhere this is like not when the earth is cooled, when the rock is formed, the mineral is formed, maybe after the volcanic eruptions or something like that, whatever happened, and then we have the quartz, maybe, or maybe they come on the surface, the silica, or maybe the basalts or something like that, when they are exposed, and then we have the first form of water. So this is quite interesting, because these are the questions children are going to ask, and if we say that earth was formed 4.5 billion years, then we don't know when water was formed, and then maybe around 3.5 billion, as we have the oldest 3.8, we have the oldest water being dated in Canada, and then 3.5 you dated this something here in Australia, and all these questions, yes, these are the data, but how we interpret it to make it conclusive, so that it is understandable to the children level, and then after this, as you rightly said, that the forums gradually, from single cellular organisms, they keep on becoming, by the time Paleocene and Eocene, they become very large, because in Sabatu in Himachal Pradesh, that is very near to my this museum where we are building, we have got large foraminiferas also.
Right.
Yeah,
Yeah.
yeah, maybe 1 or 2 centimeters, or maybe larger than that also.
Yeah.
And
Yeah.
then we have discocyclina. There are varieties of it, but and then there are oysters communities. But I think your presentation, and if you can maybe I don't know whether Professor Bhatia was very much doing this work. S.B.
I
Bhatia.
think one of the things that's sort of worth remembering is that the the earliest forms of life, you sort of mentioned, well, how did it get on Earth? And there's this theory, that you might have read about called panspermia, that all the amino acids are floating around in the universe, and probably they get transported around the galaxy and on asteroids and things, and then sort of rain down when they come into contact with the outer atmosphere. And of course, all of these, they then might develop into sort of more complex, what we call life forms. But nearly all of these are going to belong to that group of organisms, or that large group that we call extremophiles. In other words, all the um, very difficult things to study even today. Studying modern sort of extremophiles is difficult enough if you're sort of looking at white smokers in oceans and things. And of course, we sort of, I've demonstrated, and you've seen, yes, looking at fossils, and children of all ages can recognize something that is a fossil, or when it's explained. But we know very little about the fossil record of extremophiles. These organisms which live sort of on the boundaries of chemotrophs.
Mm-hmm.
These organisms that don't need sort of the same oxygen and water that most of us living within the normal biosphere do. But these sort of really strange organisms that might live in sulfur-rich environments, or down the bottom of deep mine shafts and things. And not only do we not know much about them at the moment, but we certainly don't really understand their fossil record. And I think there's two aspects we've got to sort of really look at. One is exactly what sort of extremophiles there are out there. And the other is how can we detect these in rocks?
That is the most important and the most challenging question,
In the stratigraphic column. And as I say, doing that for the last 500 million years might be something that is achievable. But the minute you start saying, well, I now want to go back into the Archean, Precambrian rocks, that's when it becomes really, really difficult, because even some Precambrian and Archean terrains, which we talk about as having not undergone a lot of structural sort of alteration or overprinting. I mean, they are still incredibly old sort of environments. I mean, we often used to talk about this, and when we were out in Australia, that they would say, well, the environment, the topographical environment we're looking at in the Pilbara looks very similar to what it might have looked like, in Precambrian times, because the plates are very stable. But of course, they've had billions of years of weathering and sort of just mild, just alteration going on. And it's really difficult to sort of work out, what was happening, and what's an overprint of an overprint of an overprint of the history that these areas have gone through. As I say, you're looking at a part of the fossil record which is not really, which is the most difficult part to sort of work out and study. So it's not a nice clearly defined.
So another question which is coming in my mind is the specimen. Who picked up that specimen which you were able to date to 3.8 billion years, and how you just jumped on that discovery?
Well, it was originally described by a gentleman called Bill Schopf, who was an American paleobotanist. Well, his father was a paleobotanist. He was a paleobiologist who worked on Precambrian terrains, and he's written a number of books on this. And he happened to do this work in London. So he was visiting from California and did this work in London. And then when he finished the work, he bequeathed the samples to the Natural History Museum. And so it came about with, I was, Martin Brazier said to me one day, how would you like to see the world's oldest fossils? Yeah, I don't, yes, of course I want to see the world's oldest fossils. Well, they're only 60 miles away from us. He said, I'm in London. Let's get the bus up there. and can go to the museum and have a look at these. And this was in, say, the late 90s. The material had been published, I think, in the mid-90s. And the surprising thing was that all the Precambrian paleobiologists who had obviously passed through London and probably visited the Natural History Museum, when we asked to look at the material, someone said, "Oh, no one's ever asked to look at this material before," and it had been in the museum, 5 or 6 years, and you think, wow, that's incredible. I was thinking of all the paleobiologists who must have passed through and sort of had taken it as read that yes, this is the oldest fossils, but no one had re-examined them. And so I think when we started doing that, it came as a bit of a shock to a lot of people that, first of all, you question what this very eminent paleobiologist has done, and then you say, or then your conclusion is that they're not biological, that they're not fossils, that they're mineral artifacts. I mean, that's we did really question this. I think for a few months we sat on this thinking, should we go ahead and publish this or send it out for review? And it sort of threw a real spanner in the works. But of course, from the Archean material, you then have to wait something like nearly another billion years before you get to genuine material, which can be demonstrated to be sort of, algae and microfossil material. So there is this problem with trying to work out exactly what you've got there. And the original names given to that Bill Shopford used, he'd given them both generic and specific names, which again is absolutely fine, except the biological clocks at the time wouldn't take this, finished before they got back to this material. So it really was, that in itself was a bit of a problem, particularly when you, as I say, start erecting, species names, and you're using generic names for something. You do have to be very careful with that. But if you can't then trace them back in time, that's a real problem. You've got to address that.
Now I come from Australia. Let's come to the Spongtong ophiolite and your findings there, and also
I must apologise for my pronunciation of it in case I...
No, it's okay. It's okay. We all understand that. And then probably that ophiolite belt in the and in the vicinity of that you are getting this all forums,
Yeah.
In the limestones which were part of
which overlie the whole lot. Yes. So you had all this tectonic activity going on, and the ophiolites were being formed, and then there was this sort of large, fairly extensive tertiary marine sea that was over the top of it. So now, following obviously continued uplift, so you're left with just carbonate bits on the top of a lot of the mountains out there. And when I first went out there with Mike, he sort of said, "Oh, come out and see these and see what you think of them." Okay, so where are the fossils then? Well, they're up there at the top of the mountain. What? It was so. I initially spent 3 months out there as we did these treks around the ophiolite, collecting the tertiaries. And when I got back, he said, "Well, yes, fine. Can you date them?" yeah, we can probably, I know the tertiary. That's not a problem. Well, can you put them into, how accurately can you date them? Well, it's very difficult with larger benefits because there is no scheme for doing it. And it was only after I think I'd been working on them for about 3 or 4 years, getting the sections prepared, examining them, and then I sort of came across this scheme which had been used in the Adriatic and the Mediterranean and sort of Alpine terrains, and I thought, oh, that's the tool that I can, I'll try and apply it to what we've seen in the Himalayas, and yeah, sure enough, it sort of worked. So actually getting a much better date on it. So yeah, it sort of fell into place. I have got similar. I've got more material to sort of look at, but basically the story has, no matter how many, no matter what other people have done, I don't think anyone else has come up with a different date using the same sort of technique. You can sort of refine it a bit, but actually it's all done on the assemblages. You're not looking at one particular species, because these assemblages are all they're intermixed. You get this is something which I hadn't really fully appreciated until I started this. That when you might be able to show that your nubulites have evolved from one species to another, but actually within an environment you get all of them occurring at the same time. So that was, again, sort of another eye-opener for what forams are doing here. You don't tend to get that with planktonic forams, which is why zonation schemes, biozonation schemes for them, for calcareous nanofossils, and even for ammonites, zonation schemes with ammonites are a lot easier to use because we're usually only tracing the first appearance and
The last appearance
as well, and constraining it within there. It's not quite the same with the larger benthic forams. Yeah, I'm always interested to see what other people.
So now, yeah, another question which is coming in mind is like all these fossils which you're getting in Zanskar, and also we are getting some the Eocene specimens we are getting now. I also happened to go to Zanskar, and then I posted you, I think, I mailed you one specimen, that is from Zanskar.
Right.
So these forums, and then we have these forums. What do you in Eocene also? In maybe we'll send you the specimen now. Very soon.
Right.
We have found this very close to the, you can say, 20 million years. So maybe this may be around, must be around 33 or 34 million years.
Okay.
So just at the, you can say, the Oligocene contact. So we have the, in the smallest we have this, the green fishes, the red fishes, and the sandstone fishes, and then in this green fishes, this is which we consider to be Eocene, Paleoeocene, marine sequence. Then we have this Oligocene, this continental sequence, and then the grey sequence, where we have this lot of palm fossils and all wood fossils, the channel fishes. So in this context, so approximately this 20 million, 23 million years, then 33 million years. So at that contact, we are getting this Eocene now. We'll be sending you some specimens of this. And then also the one which you showed at the Indus suture, this in the suture zone near Chilling, we have got very good forums, and then also so that aspect taking into consideration. And what do you say, like is the similarity with the fossils which you're finding here and fossils which you're finding in Australia or the contemporary formations at that time, or maybe Indonesia, Malaysia, or maybe Africa. No, not yeah, maybe. So,
Yeah.
what is your view of the paleolatitudinal position of these fossils? And because maybe yeah, they're widespread. One thing. Second aspect is like even if you're getting it in Zanskar, but do the paleolatitudinal positions suggest that they can be survived in those cold winters or not? That is an important question. These forums.
Yeah.
So because
Yeah.
if we see the paleolatitudinal positions of these Zanskar and Spiti regions, so probably 30 degree, 32 degrees north of equator, and then probably extreme temperature, extreme maybe conditions, and then so probably what we are trying to prove, it is not prove, but what we found, I just want to share that the concept, because you and Surley, I can associate my findings with you. So basically, we found very interesting fossils of plant fossils from Kasoli. That's near the town where we are building this museum.
So
So
we've had a talk from another former colleague of mine, Bob Spicer,
yeah, yeah,
I think.
yes, yes,
I
yes,
think,
yes.
yeah. I worked with Bob. Well, I worked with him when he was at Oxford for a
Okay.
while.
Hmm.
But I knew him before I came to Oxford. We worked. We were in different departments, but in the same building in London.
Hmm.
When I worked there in the 80s. So yeah.
Achha, 80s you met him, huh?
Yeah. Early 80s.
So around 89, I think he was in India, when I was completing my master's,
Right.
90 or maybe 91.
Right.
And then he visited my collection, in Kasoli.
Right. Okay.
Yeah,
Yeah.
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 He was quite interested in the findings,
Yeah.
because all these fossils suggest that the Himalayas at that time, or now what we are trying to establish is based on the findings that these paleolatitudinal of the Himalayas.
Yeah.
Maybe because the sea which you have showed very, very, very interesting. The slopes, the continental shelf, and then the basal plain, and
Yeah.
the basin. Basically. So
I think.
I really admire that slide. And
Yeah.
then if that environment is equatorial, or whether it can they can exist to the present latitude position, that is a question mark. So
Yeah.
I think best explanation could be if they are more near the equator, warmer conditions, and then the entire concept of the timing, because how then that basin moved further ahead north, that has to be transported. That is an interesting question coming
Yeah.
up, and what is the relationship between the forums which we are getting here and the equatorial foraminifera? What are your comments on that?
Well, I think nearly all the shallow benthic forams, larger benthic forams, are pretty close. A low latitude
Low latitude,
uh,
yeah,
assemblages.
yeah. Because for one reason, what I think is the more the size has to grow, it has to be near the equator. The more
Yeah.
lesser the size, then we move further. Maybe that is the colder conditions, and maybe the to save the
Yeah.
energy, the animals may evolve in that matter. I don't know what are your expert opinion on that.
Well, again, it is unusual with some forams. You often wonder why certain organisms become large. Do they become large because there's a good food supply for them, or do they become sort of large because they're in a stressed environment,
Mm-hmm.
and therefore they'll become large because they'll just try and absorb as much as they can. And I think with I've often thought with foraminifera, regardless of well, particularly with the larger benthics, but sometimes with some of the others, that they're actually often the first organism into an area, marine-wise, when you're talking about the invertebrates, and they're often the last organism to leave that area. In other words, they will do everything they can to stay on and grow or to survive in that. So you often get a lot of growth deformities with them. And I noticed this when I was in Florida Bay, even in a small area. Clearly, there was a lot of fresh water used to flow through the Everglades into the bay. That's nearly, I wouldn't say completely dried up, but there's certainly more and more of that water is obviously being taken off to, say, function, go to the large conurbations like Miami and St. Petersburg, which are in the southern part of Florida. So you're getting a much more, you're getting less fresh water coming in, so you're getting a much more stressed environment now in the bay. And you would often see some of the forearms would show these quite unusual growth deformities in that rather than being a planispiral form, they would then show a growth at right angles to that. It was quite bizarre, so but they were still surviving, but were obviously in a very stressed environment. And that sort of fascinated me as to why forearms will do this. With other larger, say, invertebrates, like corals, if the environment is not right for corals, then they just won't grow there. They die off. And I think with some of the other organisms, that might be the case, that some of the mollusks or whatever, you're not going to see them if the environment's not right. But with the foraminifera, and it might well be the same for, I don't know, ostracods or something as well, particularly as they can survive both on there's terrestrial forms and brackish and then marine forms. So it may well occur with them, but once you start getting a stressed environment, these organisms will, as I say, the forearms will try and cling on.
Yeah, that's great, because the slide which you showed that they occur at around 3,500 meters depth.
Yeah.
And also near the coast and the shore and everywhere they can just adapt, and they can just modify, what do you see, according to the environment they just grow, or how they evolve, the same forum.
Well, they have a very complex life cycle. Again, this is what which is what surprises me. They have this life cycle which can be both have a sexual phase in it, but they have a lot of asexual phases, and you can get this sort of there was a lot of work done on this in the late 1950s by a chap called Hofka, I think, who did all this work, all these studies where he looked at where certain forearms will have this sort of trimorphic life cycle. So they will be working away, they will be sort of going through this asexual phase, and then suddenly there might be a sexual phase. And I guess it's all to do with if that environmental niche will support it, and if they can flourish in it, or if they need to do genetic sort of, have some sort of genetic modification. But it does mean that even in the asexual phase, they can obviously keep on producing and keep on generating.
So I think they are the most, listening to your talk, makes me feel that the forums are the most interesting creatures ever lived on this planet Earth.
Absolutely.
And they are the most fascinating creatures, adapting to each and every environment, making all the permutations and combinations, and I think in a way much superior than man. we may be struggling because of this coronavirus, and we may be struggling. But I think these forums more or less gets a chance to adapt to different environments and just Cling on,
That's
cling on, and then keep on permutations
yeah,
and combinations and just keep on modifying certain things and just giving a new
yeah.
species after fighting all these odds.
Well, as I say, I think it's quite strange that that you can get, within the same rock, you can get these ancient forms of it with the so-called, later evolved forms, and you think, well, that I can't think of any other species of higher organism and even lower where that occurs. I just think that's quite incredible, and so yes, they're not brilliant for sort of just using a species as a biozone, as a biofossil,
So now,
but we're no good for that.
so now
Uh,
this is now making me sorry. This is now making me quite. So now we need a section on forums now. One section has to be dedicated in the museum, right
yeah,
from the Paleozoic or the Precambrian or the whatever we may call it, the unicellular organisms, how they evolved, or how the unicellular organisms evolved, and how the unicellular
yeah,
organisms went to multicellular, and how they have been adapting to the present forms, experiencing all these ice ages, glaciation, the great oxidation ages, volcanic ages, meteorites, asteroids, you name it, and they survive it.
yeah,
So
yeah.
let's let's
That's right.
let's I think let's make it a section in the museum. And I think now after listening to your talk and having a great discussion with you, my love for forums
I,
have grown enormously now.
good, good.
And now I think I need a section, a small section where I think we will show that what what is going to
Yeah,
happen next is how the forums will decide, how they are going to modify and tell how they are going
yeah,
to.
yeah, yeah, yeah. They are incredibly adaptable, and I mean, we can learn
So
a
I
lot
think
from
I
that.
think children will love this story.
Yeah,
Children are going to love this story. So maybe I can share you the museum visuals, and then we can make it something very simple. And I will love, because we are just concentrating on the Himalayas. So we would like to
yeah,
have
yeah,
specimens. We have got some specimens, beautiful specimens of forums, larger forums, and then from Zanskar also some one or two specimens. So we will keep it. But I think we will make a good small chart for the children. Highlighting
yeah.
highlighting the
Absolutely.
highlighting love for forums, and then the next aspect would be the last. Maybe this could be what I would like to ask is the what do you say about the gas hydrates, and is there any relationship between forums and the gas hydrates, or yeah?
That that I don't know. It was I only did a small. My contribution to that study was quite small. Um, was a lot. It was a long time ago now. So we didn't actually look at biome. In fact, that's one of those weird things where um, we did this sort of work on it, and it was all based on a lot of the I think what my colleague Steve at the time, Steve Hesselbo, was working on there was from Yorkshire. And anyway, I prepared some material, and we originally submitted it to the journal Science. And after a few months, we got feedback from them, and they said, no, we're not going to publish it. Okay, that's fine. So I think it was about another 6 months after that, Steve said, oh, I'm going to resubmit this, but I'll submit it to Nature instead. Um, he said, and I'll just keep the same authors on it because we all worked on it, but he said, we're not actually going to be using we won't need the techniques bit that you prepared for us. Okay, that's fine. But he very kindly sort of kept me on that paper. But yes, I think out of all the papers, that's probably one that is getting more citations than anyone else because no one else had thought about it. And, the gas hydrate problem at the time and the fact that these were sort of huge storage areas, in the I don't know, in the stratigraphic column or in the ancient, in the seas at the time, and no one had really sort of put this put this together and thought about this. So I don't claim to be in any way an expert on that. I just happened to be there and supported him at the time when we were doing this work. Um, but yeah, I have looked at been absolutely fascinated by. As I say, I think that paper is cited almost every week. I will get a notification saying
That's
someone has
great.
used
That's
this
great.
paper in there, and I think, wow, that's really
But
good.
gas hydrates have been commercially exploited somewhere, or it's still in the process.
Yeah, I think it's still in the process, isn't it? I know he was looking at it. I mean, primarily at the time, he was coming at it from the point of view that it might lead to I don't know, a local extinction or something. When you're getting all this sort of hydrate released, and there were reasons as to why it was being released, and of course that's still very relevant today. If there's, if you're not careful with some of and you alter certain environments with perhaps it's a deep sea brine holding everything in place in the ocean, and if you're not careful and if you upset that, then it could release these hydrates into the environment. But yeah, I mean, I think it's just probably another example of why it's important to study earth sciences and look very carefully at these ancient processes that have been going on, and just, what is, if we're not careful, they can induce something in climate change that could be quite catastrophic to the survival of species on planet Earth. So yeah, it's an area that needs more work. And yeah, yeah. But
So it was
all
great
right.
talking to you, Owen, and thanks for sparing your valuable time.
Well, thank you for getting back in touch, and I'm sorry it took so long to get
No,
things
it's quite
all
interesting.
straight. So
I think we need to be in touch with each other, and
yeah,
I appreciate if you can if we can just make a small, not a very detailed foraminifera, but write some very interesting facts about forums and just make a poster
yeah,
of it, and then just I like to display it maybe of any size with the man. The man is coming, and they have been coming from maybe, I don't know, maybe they are the oldest living creatures on this earth now, because
well,
from single cell, and then earlier they may be
I
some single cell, or they may be some acids, maybe some amino acids, and from amino acids how they evolved into single cell, that is also a story.
yeah,
So maybe
yeah,
they are the oldest organisms living on earth, and they are still existing today, and that completes the story of our entire evolution.
yeah. They are
I think,
fascinating.
yeah, yeah, yeah. So and thank you very much, Owen. So maybe
No,
these Zanskar
I'm
oysters, which
sorry. I have no idea what the time is there. It must be quite late now.
yeah, yeah, it's now not very much, but it's like 9:15.
9:15.
It's
Oh, right.
okay.
Yeah,
Dinner
yeah,
time for
yeah,
us.
yeah. I have to. I'm preparing another talk at the moment on my um, on the map maker William Smith, who is someone else who really fascinates me, and I'm often asked to talk about this. How the first geological map came into existence, and this person who had no formal education actually came up with this idea, and nearly all the geological maps we see today have something in common with what William Smith was doing.
Yes. Very right. So maybe when the museum starts, we record more of your talks, and
Yeah,
whenever you
I,
have an opportunity,
I,
please do come to.
I
Uh,
have looked on the map where you are, and looked at the museum. It's a lovely building, actually. I do like the sort of the building you've got for it. And I
yeah,
thought,
we have
wow,
not used any wood, in the museum.
yeah,
No wood.
no wood.
No wood.
Oh, oh, right, okay.
So it's going to be a very very interesting experience for anybody, and I want to complete
Yeah,
this entire journey in about, say, any children coming, it completes the entire journey of 3.5 billion 4.5 billion years to
yeah,
present day.
yeah,
Stone tools also we are keeping, and there's now this forums with this interesting headings,
yeah.
we are going to make some very interesting poster of that,
That.
place it there, and we have fossils of forums. So I think this is going to be a very very interesting.
Yeah,
Now forums are going to be an interesting part of the museum. Thanks for.
yeah.
I'm so happy. So now I
So
invite Professor Kishan Kant to just say a few words and conclude the session.
thank you, thank you.
Yeah, Dr. Arya, thanks a lot for giving me an opportunity to wind up the session now. And Dr. Owen, of course, a very richly endowed this session that you have given. I have been a patient listener, and it was, of course, really interesting listening to both of you in discussing the various forms of literature as it is emanating out of the practical experience both of you have. So it was wonderful listening to you both, and I hope that I would be lucky enough to listen to more such discussions in the future. So I think that this was an opportunity for me to listen to the great scholars, Dr. Owen and Dr. Ritesh. Both of you have immense contribution to the field of geology, and that is what I have today gained out of this discussion. Thanks a lot for being here. Hopefully, we'll be seeing you soon. Just like Dr. Ritesh has said, we'll be seeing you in Tethys Fossil Museum, and we would wait for you anxiously. And we want that you should be there and enrich us with your experience. That is live. We would love to listen to you. Thanks a lot for being here.
No, thank you very much.
Thank.
I really enjoyed it.
Yeah, we really enjoyed it. We really enjoyed it. I think it was real. You were able to inculcate the entire love of world forums with us, and I
Yeah,
think we need to clarify a few aspects now about evolution, and then we may have a separate talk where you can show some specimens and how you did it, the separation for the earliest fossils, and how these forums which you find in Sanskrit should have been in a lower altitude, not at the present altitude we are finding. This could be the, I think, very interesting
yeah,
findings of
yeah.
your talk, which we have just heard from you. So
Yeah.
thank you, Professor Owen.
Thank you.
Namaskar. And I think today is the birthday of Mohavik. The boundary between his birthday is today.
All right.
Yeah, yeah. Okay. Thank you very much.
Thank you.
Thank
Take
you very
care.
much.
Thanks, sir. Thank you.
Namaskar. Namaskar, sir. Namaskar.
Bye bye.
Bye bye.